Hi there, and welcome to another episode of The Science Hutch. I'm Hutch, and our very special science today is all about projectiles, objects that are in motion under one force and one force alone, and that force, my friends, is the force of gravity, which will be always pointing towards the center of our planet, the wonderful planet Earth. Now, if you're not watching this from Earth, then some of this information is going to be different for you, but the physics should be the same as long as you are still in our universe, the universe on which Earth exists right now in Earth time 2020. All right, so here's the deal. The way this physics works is that an object in motion will remain in motion unless acted upon by an external force, okay? So the idea that if I throw this ball forward in space with no external forces on it because Earth is not near us at that point, I'm way out there in space, this koosh ball will continue to just go forward at a constant velocity, whatever velocity it left my hand with, forever, or until it encounters something else, which it probably won't, because space, friends, is spacious. It is vast, and a lot of us think, well, eventually it'll fly into the sun or something, but probably not, because there's a huge amount of space out there. So it probably won't ever hit anything for like millennia, and it'll keep going at a constant velocity. But on our planet, this forward constant velocity, that's true, because that's going to continue to happen. The only other thing that'll happen is, let's watch it. Here we go. It went, like a, It went, let's see it again. It went, It went in a shape that was a curve. The reason why it went in a shape that was a curve was because it kept tracing out a forward velocity that it left my hand with. That was constant, but it had a downward acceleration, an acceleration that to me is down right now because the center of my planet is down to me right now. And so the center of the planet was pulling this object closer to it with a constant force, that force of gravity, which we typically call this object's weight, W-E-I-G-H-T, weight. So the weight is a force, and the object's mass is the atoms in it, and that's a difference between weight and mass. The atoms in this koosh ball are attracted to the atoms of the Earth, and they really pull each other together, but we don't notice the Earth coming up to the koosh ball because the Earth has so many more atoms that those atoms kind of resist the motion, which we call inertia, resisting a change in motion, more than the atoms in this koosh ball. But I digress. Inertia is a concept for another day. All we need to know right now is that this object will keep on moving forward at a constant velocity because there's no force to speed it up or slow it down in that direction. There's air resistance. Okay, there's some air resistance as it hits the air molecules in front of it as it moves forward. But that is not enough to be really measurable in this experiment. Like in this experiment of just throwing an object, it is what we call negligible. Negligible meaning you can neglect it and you can ignore it and you can still pretty much figure out some cool things about the koosh ball, like where it will hit the ground when it eventually hits the ground. And it fell like beyond my desk to the ground. So where it's going to hit the ground, when it's going to hit the ground, how fast it's going to be moving when it hits the ground, all of those things we can predict. And that's pretty amazing if you think about it, because we are actually predicting the future. It hasn't happened yet. I might throw it. When I throw it, it probably is going to hit the ground. Like, if experience is anything to draw from, every time I've thrown this koosh ball, it's always fallen to the ground. But now I could tell you, before it ever leaves my hand, if I just know a couple of small things about it, I could tell you when and where and how fast it will hit the ground using some mathematics. And we don't even have to use super fancy mathematics. We can use algebra to figure that future out. So I love this. It's super fun. And let's look at how to attack puzzles that involve projectiles. The first thing we need to understand is we need to understand the situation. You always need to understand your situation. So what's going on with the projectile? Is the projectile moving solely up and down? So we would say like in one dimension. A dimension is a direction in our three-dimensional or three-directional space that we live in, okay? So up and down we would typically call the y, the letter y, the y dimension. And we steal that from mathematics, where they use the y-axis for the vertical axis on a graph. And then I was going to steal from mathematics as well for the horizontal, or the left and right dimension. That's going to be the x dimension, like an x-axis on a graph. The one that's new for most of us new physicists is the z dimension, where we're looking at an object that will go forward and backwards, and on a piece of two-dimensional paper where we do most of our mathematics and problem solving, that would be into, like whoosh, right through, into or out of the page, into or out of the page. So, and that's the Z. So we have X, Y, Z, the last three letters of the English alphabet. X horizontal, Y vertical, Z into and out of the page. That's how we would write it if we're doing like some kind of crazy test, like an AP exam or something like that. All right, so now how do we work with three different dimensions at once? Well, here's a quick trick. If you have a projectile that is being launched at an angle, whoosh, 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 like at an angle that is maybe like 45 degrees, whoosh, like that, boom, okay? 45 degrees from what? 45 degrees from the horizontal, or maybe the ground. So you have to decide, okay, 45 degrees from the horizontal or the ground. So that's where we typically measure the launch angle from. And then we have to break that up into two different dimensions. Well, what if you're moving like this, and then you're like, so it's kind of coming like towards you and moving up and down and forward. So it's got all three. Well, all you got to do for that is just reorient your frame of reference or your perspective. Okay, so if it's like this, it's oh no, it's got all three. It's like kind of went out of the page a little bit. Well, let's just go turn your camera, people, and now you can watch it go the exact same way, but it's only forward, like only the X forward horizontally, and then, or from your perspective, that would be what, like to the left or to the right, and then it's going up and down at the same time. We don't have to worry about the z-axis. So we can always boil down our projectile motion into two dimensions, and we'll just use the x and the y. Now the last thing we got to know about that is that when you're working with mathematics, with the kinematics equations, those are the equations that deal with constant accelerated motion. Kinematics is a crazy word that just means constant acceleration. So the equations for kinematics are the equations that mathematically predict how different variables like speed and acceleration and position and time, how all those different variables affect each other or don't affect each other for an object under constant acceleration. And where's the constant acceleration coming from? For projectiles, that's right, gravity, the constant force of Earth's gravity. So there's only one force we need to think about. There's only one acceleration, and lucky for us, that acceleration is the same acceleration no matter how big or small the object is. As long as the object is massive enough, and massive I mean has enough atoms, to cut through our atmosphere. So a feather is not massive enough to really cut through our atmosphere without kind of floating and having that constant acceleration of Earth's gravity be lessened very quickly to what we call a terminal velocity. Terminal meaning final, or the end. You've been terminated. You've been ended. So the final velocity of a feather is very slow, or a very low value in meters per second, and so the feather will reach that quickly. We don't have to worry about that in typical projectile equations. All right, so in typical projectile work for introductory physics, you're not going to have to worry about terminal velocity, you're not going to have to worry about air resistance as a force that you have to bring into play. You're going to call that negligible, and you can neglect it. It's neglectable. All right, well, now you know the basics, the ideas, the concepts around projectiles and their motion. So now we just need to be able to put some numbers to it, and then you're going to be a master at algebraically manipulating the mathematics around kinematics and projectile motion. Let's get to it. Let's go do a practice problem. I'll see you over on the next video for that. Thanks for watching, and we'll see you over there for a practice problem. Bye-bye.